Okay, moving on. Problem 5. We've got students pushing a large crate across the floor of the classroom. So there's our large crate. And let's see, the one student pushes on the crate with a force of 250 newtons directed at an angle 20 degrees below the horizontal. So what that really means is he's pushing down like that, right? And this is 20 degrees here, 250 newtons. And then the other one is pulling with a force 350 at an angle 25 degrees above the horizontal. 25 degrees, and there's doing 350 newtons. Okay, and so sketch the scenario and draw the FBD. Oh, so this one actually says sketch the scenario. So there's your sketch. Now let's go draw the FBD. So there's one force, which is already 350 newtons. We'll just, we know that. Another force is coming like that, and that's our 250 newtons. There is our weight, so this is going to be m times g, and our normal force, keeping it from falling to the ground, remember? And then right here we have a force due to friction. So there's our frictional force, normal weight, and this all looks pretty good. So let's go ahead and draw us a free body diagram. FBD for the crate. Yoink, yoink. Okay, so coordinate axes, x, y, y, x. And then we put a dot to represent the crate. So here is a normal force. Here is our weight. Here is our force due to friction. And then we have this pushing force, which is 20 degrees below the horizontal. So I'm going to draw a dotted line in here for horizontal. There we go. So there's our 250 Newton force at 20 degrees below the horizontal. And up here is our 350 Newton force at 25 degrees above the horizontal. Okay, well, let's just do our second free body diagram then, right? So normal force comes right over, weight comes right over, there's force from friction, and then going to the right, I'm going to do this upper force first. So this is going to be kind of a tight fit. 350 newtons times, I actually have to move this over a little bit, so let's see if we can, yoink. Okay, that works a little better. So times cosine of 25 degrees. Hope that fits. All right, that's this force, and then here we have 350 newtons times sine of 25 degrees. Okay, and then below we have this force, which gets broken up also, 250 newtons times cosine 20 degrees. And down here, this is 250 newtons times sine of 25 degrees. Over, finished, done. All right, so let's move on to problem 6, which is this horizontal force holding a small block at rest on a frictionless surface. Hooray! So let's see, here's our frictionless surface slope, just like that. Angle theta there. Here is our block, mass m. Horizontal force is F. No friction. Yay. So that makes things a little easier. So, as usual, weight, mg. We've got this force here, F, we've already got, unsurprisingly. The normal force is going to act like that, perpendicular to the surface. And if we have no friction, then that is really it. Now we want to use a coordinate system with one axis parallel and the other perpendicular to the surface. So that means we're going to do this, x and y. The reason why we like to do this is because when we write equations of motion, it makes things a lot easier when the object is just going to move in one direction. So let's do this, and here we're going to redraw our coordinate axes. I like to show how much they're tipped. That's by an angle theta. So this whole thing has been torqued counterclockwise by an angle theta to match up with this. Okay, so something like that. There we go. Okay, so first free body diagram. We have the normal force going this way. We have gravity going down. And we have our applied force going this way. Easy enough there. Now let's break it down into components. So we're going to draw our body again. There's our normal force. Now our applied force is going to be broken down because it's not along this twisted XY coordinate plane or coordinate axes. So I'm going to draw, little dashed lines or dotted lines for our coordinate axes that we don't have. And this angle is theta. This angle is theta because it's been twisted counterclockwise. The coordinate axis it's gone treek, and or down here it's gone treek, treek. Okay, so F, the component of F going along the along the x-axis, which is along the direction of the slope, is like this. So there's our F cosine theta, right? Because it's from this theta, it's theta from this this angle there, or from this axis here. And then down here we have an F sine theta, and then here mg is theta away from this downward axis. So there we go, mg cosine theta, and then here we have mg sine theta. There we go, and that is all we needed to do for that one. All right, so last problem, last but not least, is 3 astronauts pushing an asteroid around. So you got asteroid, and you've got this thing, and you've got one astronaut here, and jetpacks and stuff, one astronaut here, and one astronaut here. Okay, so and then they actually give you an axis to use, which is uncommonly generous. So let's see, F2 comes from that astronaut going that way. F1 comes from that astronaut going that way at an angle theta 1. And then they say F3 comes at an angle theta 3 F3. So there we go. This is a horrible drawing, but hopefully it gets the idea across. So FBD for the asteroid. Okay, so we're going to do this X, Y. There is the asteroid. It's represented by a dot. And actually, I'm going to bring the dot over here. And F2 is going horizontally. That makes a nice place to start. And then F1 at an angle theta 1. And then oh, come on. There we go. F3 goes at an angle theta 3. Okay, well, that's not hard to work with. So let's just break it down into our X and Y. Oh, come on. X and Y components. There's no gravity, of course, because, hey, we're in space, right? Ain't no gravity in space. Don't got to deal with that crap out here. Alright, so there is F2. Going to the right again. And then we take this one and break it up into components. Theta 1 is the angle between F1 and the x-axis. So, come on. Horizontally, there we go. F1 cosine theta 1. And also horizontally, F3 cosine theta 3. And here is F3 sine theta 3. Theta 3, come on. And up here is F1 sine theta 1. Man, that was an easy homework. Easy, easy, easy. So, and this test should be easy. This quiz coming up should be easy. Just remember the rules for drawing free body diagrams. You want to have your axis. The body itself is a dot. You do one with the raw forces, all of them pulling outwards, and then you do one where you've broken the forces up into components. If you do that correctly, draw separate arrows for everything, make the dot as big as it has to be to get all those arrows out. Just remember that stuff, and I think you'll probably do fine. Anyway, good luck with the quiz tomorrow or Friday, whenever you do it.